So, on to the basic steps. There are a number of different stages in software engineering, and with the different methodologies, the interplay between these stages is different, and also the way in which the stages interact with each other and the order in which they appear is a bit different too. But the commonality between all of these approaches is that there are 6 basic components: a requirements analysis, software design, implementation of the software, integration of this software into existing systems or integration of small components, the testing to ensure the validity and verifiability of the software, and then deployment and maintenance. So what I'm going to do is I'm just going to quickly spend a couple of minutes on each of these different points. So for the majority of you, you took G51 Rec, the requirements module. So a lot of you got a head start in understanding how to do requirements. What we looked at in this course is not just capturing requirements in general, but how to capture requirements and how to detail these requirements within the context of software engineering. In order to do this, we looked at how to create software requirement specifications, which are a particular subset of the field of requirements. As you might remember, the IEEE, so the standards body for computer science, developed a standard for developing software requirement specifications. Let's see how many of you can remember which IEEE number it was. And what this means is that you detail in your requirements everything that you need in order to be able to go and design the software. So the requirements are a list of statements of what the project must do or what the software must do. The functional requirements refer specifically to things which are part of the functioning of the software. The non-functional requirements refer to things which form the context of the software. So in the context of our games, for example, a functional requirement is as the left arrow key is pressed down once, the sprite moves left once, right? A non-functional requirement would be the game is enjoyable to play. Functional requirements have to be testable via some form of formal test. And what you do at the end of a project is you test based on the requirements that you've listed. So you end up with a software requirement specification which allows you to produce a design. This design can be at many different levels. You might have your architecture design, so how your system works overall. You will have algorithm design for how certain parts of data need to be tracked within a system, or for how events are handled within a system. And you might have function design or class design, dependent on whether you're using an object-oriented methodology or not. So the software design has to be detailed enough for a developer to be able to take that design, understand it, go away and actually make the product that you want. There is some interplay between design and requirements. As you design things, you realise that certain limitations can creep in. You might want to build a game in Scratch which has a really nice 3D element and scrolling background. That might be what the customer wants. However, the constraint of using that program means it's not possible. So you might need to go back and modify the requirement specification to do that. So the design process often relies on a lot of diagrams. It can really help sort of clarify what it is that you're thinking. But like I say, the design is pretty much a bit like a recipe. It should tell the developers exactly what you want implementing and how you want it to be implemented. So the difference between requirements and design is requirements are like the ingredients for what it is that you want to make. The design is like the recipe which brings those ingredients together and shows precisely how the various different components are going to interrelate to each other, how the user is going to interact with the system, and this should be detailed enough for somebody to implement. Now, in implementation, we talked about different good standards of coding practice. Implementation is a bit difficult to talk about without referring to a specific programming language or without referring to a specific project. But in the abstract, it's taking that design and realizing it within a computational system. So either using pre-existing code as a framework to build up from the bottom, or implementing code yourself. And during the implementation process, there's a number of things that you can do in order to achieve best practice. First up, you can use version control systems. Version control systems are really, really useful, especially if you're using some sort of iterative process at developing your software, or if you have an unstable requirements specification. So version control systems can be centralized or distributed, and what they do is allow you to keep track of changes to your programs. They can allow you to produce documentation of the change logs separately and in an integrated way too. And what they can let you do is have multiple people work on the same piece of code at the same time without overwriting each other's changes. They are ideal for projects which are distributed. So if you've got half of your developers working here, half of your developers working in India, absolutely perfect. It means that the same people are not constantly emailing each other code. What happens is you have your document in a repository, or your source code in a repository. When you want to work on that particular piece of source code, you check it out of the repository, and then you work on it. Then once you finish working on it, you commit your changes and it's sent back to the repository. In a standard centralized version control system, once the document has been checked out to you, no other user of the system can then check that document out. This is the standard way in which things like CVS work, or SVN as well. Okay. So version control is really important. Adhering to good coding standards is something that I know a lot of junior developers find difficult to do. You have your own ideas, you have your own style, and you have your own way in which you want to develop software. However, if you're developing software with other people, what is the concept of ownership of code is actually unclear. You need to have a standard by which the entire team can work. So you agree things like how to treat white space, where to put brackets, how to develop a schema for naming variables. So on the surface of it, these things don't necessarily look like they make much difference to the code. What they do is they increase the readability of the code. And if a code is easier to read, then it's easier to modify. If it's easier to modify, then when it comes to maintenance and refactoring, it's going to make quite a large difference to what it is, or to the quality of the code, and to minimizing the redevelopment time. Also, it means that bugs are easier to spot. So you can spot a missing bracket much easier if you know where to expect that bracket to be. Simple stuff. Also, because you might want to work with other people on stuff, it's good practice to comment your code. And comments doesn't just mean one big block at the top saying this class is designed to do X. If the code for a particular feature that you're implementing is not self-explanatory, then you should put comments there in order to say what it's for. Now, I'm not suggesting you comment every line. That's just as annoying. But being able to use comments appropriately is really important. So, integration. Integration is where you've got to take a whole bunch of bits of code and stick them all together. It can actually be really difficult, and this is where the testing comes in. So while you're integrating code, you need to be testing it. And while you're implementing code, you need to be testing it. And there are a variety of different testing techniques. So if you have a look at one of the lecture slides on testing, you'll see that there are a whole bunch of different types of testing techniques that work in different types of ways. If I was you, I would revise testing techniques. testing is really important to make sure that the code does actually do what you think it's going to do, and that once you integrate some code into a system, that the system does what you think it's going to do as well. I can't understate how important testing is to the process, and I can't understate how important it is to use standard tools in order to help you do this. The beginner's or the novice way of testing software is to simply add a whole bunch of printf statements to the software, and that has its uses. So you can see what output is at certain places, and you can query output and stuff like this. So it is kind of useful, but it's quite limited. One step up from using printf statements or print statements to check your output is to use a commercial or open source debugging program. Debugging programs let you step through different parts of the program while it's executing, allow you to put watches on certain variables, and allow you to see and look inside and see exactly what is happening within your program. Now, as soon as your code gets more than a couple of 100 lines long, you're going to be chasing down bugs which you're not expecting. Buffer overflows, wrong boundary conditions on loops. Do you want to use a while loop, or do you actually want to use a do while loop? Those are semantically different. Is it giving you the right output? Sometimes these things are much easier to chase down if you're using a debugger. Also, if you go into something like scientific computing, chasing down floating point errors can also be really difficult. And sometimes your code's just too big in order to have that many printf statements. You end up debugging the printf statements as well at that point. Speaking of testing, don't forget there is white box and black box testing. White box where you have access to the code. Black box testing requires you to test the system without having access to the source code itself. White box testing often used for debugging and unit tests. Black box testing often used at something like user acceptance testing. Sometimes this testing process gets quite lengthy, therefore commercially most people tend to use some form of testing harness. There are many different testing harnesses available. The one that we talked about was the unit testing framework like JUnit and PyUnit for Python. This is a really good framework which allows you to automate the testing process. This is particularly used in test-driven development. We'll come back to test-driven development later. So once you've tested it, once you've implemented it, and you've got your requirements right, you've got your software. So the software at this point needs to be deployed. This means that you're working with the infrastructure that the customer has already given you, and sometimes this causes you challenges. Sometimes there are pieces of equipment in the system which are not ideal. Sometimes you need to do a calculation which requires a 64-bit machine and you've only got a 32-bit machine. So the code needs to be modified. Or also, perhaps the database that the client is using has changed through changes made by an external provider. You need to go back to your code and you need to modify it to do this. So this is maintenance and code evolution. That was quite a lot to say. In summary, requirements, design, implementation, integration, testing and maintenance form the software lifecycle. Different methodologies arrange these different components in different ways and have different emphasis on different things. We've talked about the different stages of this and the different tools that you need in order to do it. So I think this is long enough for one podcast. So I'm going to go and make a coffee. I'm going to let you think about what it is that I've said, and I'll come back for part 2, which will be going through the different methodologies and looking at project management.